What if I told you there are structures in space so enormous, so unimaginably vast, that they make our entire galaxy look like a speck of dust? Picture this, a single cosmic formation stretching billions of light years across, so colossal that even light, the fastest thing in the universe, would take lifetimes to travel from one end to the other. These are not just abstract ideas or science fiction fantasies. They're real, they're out there, and they're rewriting everything we thought we knew about the scale of existence. Think about the night sky for a moment. Those tiny, shimmering dots, each one is a star, part of a galaxy, just like our Milky Way. Now try to wrap your mind around this. Some structures in the universe don't just contain galaxies, they contain thousands, even millions of them, woven together in mind-bending patterns that stretch farther than we can fathom. These are the largest things in existence, cosmic titans so vast they challenge our very understanding of space and time. And today, we're going on a journey to explore 30 of the most astonishing facts about them. From walls of galaxies that span hundreds of millions of light years to mysterious voids where entire regions of space seem to vanish into nothingness, the universe is packed with wonders that defy logic. How do these structures form? What forces could possibly create something on such an incomprehensible scale? And what do they tell us about the origins and the ultimate fate of everything we know? Strap in, because we're about to dive into the deep end of cosmic mystery, where the answers are as awe-inspiring as the questions themselves. By the time we're done, you'll never look at the night sky the same way again. The universe isn't just a chaotic scattering of galaxies. It's organized in a breathtaking pattern so vast it makes the grandest mountain ranges or ocean trenches seem microscopic. Known as the cosmic web, this intricate network of galaxies forms a colossal, thread-like structure stretching across billions of light years, the largest natural formation we've ever observed. Imagine it like the roots of a tree branching out in every direction, but on a scale so immense that even our fastest spacecraft would take trillions of years to cross just a single filament. At the heart of this cosmic architecture is dark matter, the mysterious, invisible substance that makes up around 85% of the universe's mass. Though we can't see it directly, we know it's there by the way galaxies move. As if tugged by unseen hands, dark matter acts like a scaffold, pulling galaxies into these vast filaments while leaving enormous voids between them. Picture pouring syrup onto a plate and watching it stretch into delicate strands. That's how the universe's structure forms, with gravity weaving galaxies into this unbelievably intricate web. So how do we map something so unimaginably large? Astronomers use galaxy surveys, painstakingly cataloging millions of galaxies across the sky to trace the web's shape. Supercomputers then step in, simulating how dark matter and gravity sculpt these structures over billions of years. The results are humbling. No matter how advanced our technology gets, the cosmic web reminds us we're just beginning to grasp the true scale of existence. And the most astonishing part, this web is still growing, threads stretching farther as the universe expands, leaving us to wonder what else lies hidden in its depths. The Great Wall, discovered in 1989 by astronomers at the Harvard-Smithsonian Center for Astrophysics, shattered everything we thought possible about the size of cosmic structures. Stretching an unbelievable 500 million light-years across, this colossal chain of galaxies isn't just big, it's so enormous that if you could somehow travel at the speed of light, crossing from one end to the other would take longer than Earth has existed. That's right, longer than the entire lifespan of our planet. And yet, this behemoth is just one thread in the universe's grand tapestry. Before its discovery, most scientists assumed galaxies were scattered randomly through space. The Great Wall changed that. Here was a structure so vast, so deliberately arranged, it forced us to rethink how matter organizes itself on the largest scales. Picture a spider's web shimmering with dew, except instead of water droplets, each glistening point is an entire galaxy. and the web itself stretches farther than our minds can grasp. What's even more astonishing, this wall isn't solid like a brick barrier. It's more like a dense river of galaxies flowing through space, bound together by gravity's invisible pull. So how does something this immense even form? The answer lies in the aftermath of the Big Bang. Tiny fluctuations in the early universe's density grew over billions of years, with gravity amplifying them into these staggering superstructures. Dark matter played its part too, acting like a cosmic glue that pulled galaxies into these vast sheets and filaments. But here's the twist: the Great Wall shouldn't exist, at least not according to early theories. Its sheer size defied predictions, forcing scientists to revise their models of how the universe grows and evolves. Even today, it remains one of the largest known structures, a titan among giants. But the cosmos never stops surprising us. Later discoveries like the Sloan Great Wall and the Hercules-Corona Borealis Great Wall have dwarfed it in size. Yet none have diminished its significance. The Great Wall was our first glimpse into the true scale of the universe's architecture, a humbling reminder that no matter how much we learn, the cosmos always has something grander, something more unimaginable waiting just beyond our view. If the Great Wall redefined our understanding of cosmic scale, the Sloan Great Wall ripped up the rulebook entirely. Discovered in 2003 by mapping millions of galaxies in the Sloan Digital Sky Survey, this staggering structure spans 1.4 billion light-years, nearly 3 times longer than its predecessor. To put that into perspective, if our Milky Way were the size of a grain of sand, the Sloan Great Wall would stretch from New York to Los Angeles. It's not just a collection of galaxies, it's a titanic ribbon of superclusters, each containing thousands of galaxies, all woven together by gravity's relentless pull. What makes this discovery so revolutionary isn't just its size, it's the way it challenges the cosmological principle, the long-held assumption that the universe looks roughly the same no matter where you observe it from. The Sloan Great Wall's sheer existence suggests that matter isn't as evenly distributed as we once believed. Instead, it clusters in these mind-bending concentrations like foam bubbles floating in an ocean of darkness. Astronomers liken its structure to a mountain range seen from space, peaks of galaxies towering over valleys of near-empty void, with entire superclusters acting as the range's snowy summits. But here's where it gets even stranger. Structures this massive shouldn't have had enough time to form after the Big Bang. According to our best models, gravity needs roughly 13.8 billion years to sculpt matter into such colossal arrangements. The Sloan Great Wall's existence hints that either our timeline is off or some unknown force gave these formations a head start. Some theorists speculate that dark energy, the mysterious force accelerating the universe's expansion, might have played a role, while others suggest we're seeing echoes of quantum fluctuations from the universe's very first moments. Mapping this behemoth required cutting-edge technology. The Sloan telescope captured precise positions and distances for over 2 million galaxies, revealing patterns invisible to smaller surveys. Supercomputers then stitched this data into 3-dimensional maps, exposing the wall's filamentary structure. Yet even now, we've only seen a fraction of its true scale. Like tracing the outline of a continent from a single coastline, we're still piecing together the full shape of this cosmic colossus. And just when we thought we'd reached the limits of enormity, the universe whispered a tantalizing question. If this is what we've found so far, what else lies hidden in the darkness, waiting to rewrite our understanding of space itself? Just when we thought the Sloan Great Wall pushed the boundaries of cosmic scale, the Hercules-Corona Borealis Great Wall emerged, an unfathomable behemoth that makes even the largest known structures look trivial. Spanning a staggering 10 billion light-years, this titanic formation holds the title as the largest single structure ever discovered in the observable universe. To grasp its immensity, consider this. If our Milky Way were the size of a marble, the Hercules-Corona Borealis Great Wall would stretch wider than the distance between Earth and the Moon. Its sheer existence doesn't just break records, it shatters our fundamental understanding of how the cosmos organizes itself. Unlike previous galaxy walls mapped through visible light, this colossal structure was uncovered using an entirely different method: gamma-ray bursts. These fleeting, ultra-energetic explosions, some of the most powerful events in the universe, act like cosmic breadcrumbs. Astronomers realize that these bursts aren't randomly scattered but cluster in specific regions, tracing the outlines of something far grander. By analyzing over 300 gamma-ray bursts detected by satellites like SWIFT and Fermi, researchers pieced together an invisible scaffold of matter on a scale never before imagined. The pattern was undeniable: a sprawling wall of galaxies so vast it spans roughly 1/10 of the observable universe. Here's where things get truly mind-bending. According to the cosmological principle, the universe should appear roughly uniform at the largest scales, but the Hercules-Corona Borealis Great Wall defies this expectation with its sheer concentration of matter. Imagine shaking a snow globe and watching the flakes settle into a single continent-sized clump. That's the level of irregularity we're seeing. Theoretical models struggle to explain how such a structure could form within the 13.8 billion years since the Big Bang. Some scientists speculate it might be a remnant of primordial density fluctuations, while others wonder if unknown forces, perhaps even quirks of dark energy, played a role in its growth. The implications are profound. If structures this large can exist, our entire cosmic neighborhood might just be a speck within something even more colossal, a hierarchy of scale we're only beginning to glimpse. Yet for all its grandeur, the Hercules-Corona Borealis Great Wall remains elusive. Unlike galaxy clusters we can photograph, this structure is mapped indirectly, its true shape still hidden in the shadows of unobserved space. Future telescopes, like the James Webb Space Telescope's successors, may finally reveal its full extent, but for now, it stands as a humbling reminder. The universe's largest mysteries aren't just out there, they're rewriting the rules as we speak. In the vast cosmic web where galaxies cluster in shimmering threads, there exists a place so empty it defies imagination: the Boots Void. Stretching 330 million light-years across, this staggering expanse holds so few galaxies that astronomers often call it the Great Nothing. To grasp its emptiness, picture this: if our Milky Way were placed at its center, the nearest galaxy would be so distant that night skies would appear almost entirely black. No stars, no neighboring galaxies, just an endless sea of darkness. This void isn't just a gap, it's a cosmic desert on a scale that dwarfs anything else we've discovered. How does something this empty even form? Voids like this one are the flip side of the universe's structure, where dark matter's gravitational pull didn't just draw matter together but left behind vast, bubble-like regions of near-nothingness. Think of blowing soap bubbles. Where the soap film clusters at the edges, galaxies gather in walls and filaments, while the hollow centers mirror these eerie cosmic voids. The Boots Void likely began as a tiny underdensity in the early universe, a spot where matter was slightly more sparse. Over billions of years, as gravity pulled galaxies into denser regions, this patch expanded into the mind-numbing emptiness we see today. What makes the Boots Void truly extraordinary isn't just its size, it's the mystery of its sparse inhabitants. While most voids still contain a handful of galaxies, this one holds only 60 or so, a number so low it challenges our models of cosmic evolution. Some theories suggest these lonely galaxies might be tramps, ejected from clusters by gravitational interactions, while others propose they're remnants of filaments too faint to detect. But every galaxy found here becomes a crucial clue, like stumbling upon an oasis in a desert and wondering how it survived. Voids play a critical role in the universe's architecture. They aren't just empty space, they're the negative space that defines the cosmic web, the gaps that make the threads visible. As the universe expands, these voids grow, their emptiness stretching the fabric of space itself. Some even act as lenses, distorting light from objects behind them in ways that reveal secrets about dark energy. The Boots void, in all its eerie silence, reminds us that the universe's grandeur isn't just in what fills it, but in what's missing and the profound questions those absences leave behind. Could there be other voids, larger and even emptier, hiding beyond our current maps? With every new telescope probing deeper into the cosmos, we edge closer to answers, but for now, the Boots void stands as a haunting reminder of how much we've yet to explore. Its vast darkness isn't just emptiness, it's a challenge, daring us to look deeper and rethink what we know about the universe's grand design. Hidden among the countless galaxies strewn across the cosmos lies a structure so precisely curved it seems sculpted by an unseen hand, the giant arc. Stretching 3.3 billion light-years across, this mind-bending formation of galaxies traces a near-perfect arc, as if someone drew a colossal smile across the universe. Its symmetry isn't just beautiful, it's scientifically baffling. In a cosmos where matter should scatter randomly, this elegant curve defies every expectation, forcing astronomers to question whether the universe plays by rules we haven't yet uncovered. Discovered in 2021 by researchers analyzing light from distant quasars, the giant arc's existence hinges on a clever trick of observation. As light travels through space, it passes through clouds of magnesium gas surrounding galaxies. By mapping where these gases absorb quasar light, scientists pieced together a pattern, an arc so vast it would take light 3.3 billion years to travel from one end to the other. To visualize its scale, imagine holding a ruler at arm's length. The giant arc would span the length of your thumb against the night sky. But here's the twist: according to our best models, structures this large and coherent shouldn't exist. The cosmological principle, a cornerstone of modern astronomy, states that the universe should look roughly the same in all directions at large scales. Yet the giant arc's crisp curvature violates this idea, suggesting matter might cluster in ways we never predicted. It's like shaking a snow globe and watching the flakes arrange themselves into a perfect spiral, an outcome so unlikely it hints at unseen forces at work. Some theorists speculate that primordial sound waves from the Big Bang could have imprinted this pattern, while others wonder if dark matter's gravitational pull sculpted it over eons. What makes this arc even more extraordinary is its timing. Structures this massive take billions of years to form, yet the giant arc appears too young, too refined for its size. It's as if we've uncovered a prehistoric monument in a forest, one that shouldn't have been built with the tools of that era. If confirmed, its existence could upend theories about how quickly cosmic structures grow, or even suggest gaps in our understanding of gravity itself. For now, the giant arc remains a tantalizing enigma. Future telescopes like the Vera Rubin Observatory will scrutinize its shape, searching for flaws or confirming its perfection. But whether it stands or falls under closer inspection, one thing is certain: the universe keeps crafting mysteries that humble our assumptions, reminding us that for every answer we find, a deeper question awaits. Deep behind the dust and stars of our own Milky Way, hidden from view by our galaxy's brilliant sprawl, lies a titan we never knew existed: the South Pole Wall. Stretching 1.4 billion light-years across space, this colossal curtain of galaxies was only revealed in 2020, thanks to cutting-edge technology piercing through the cosmic veil that had obscured it for so long. Picture an invisible mountain range, its peaks made of thousands of galaxies, all lurking just beyond our sight until now. What makes this discovery so groundbreaking isn't just its size, though it rivals even the Sloan Great Wall, but how it forced astronomers to rethink their methods. Traditional galaxy surveys rely on visible light, but the Milky Way's dense disk blocks our view like a cosmic blindfold. So scientists turned to a clever workaround, measuring redshift, the stretching of light as galaxies move away from us. By analyzing subtle shifts in the light of thousands of galaxies, researchers mapped their motions, revealing an immense gravitational pull from something massive hidden behind our galaxy's glare. The South Pole Wall's structure is as intricate as it is enormous. Imagine a colossal sheet of galaxies, not flat like paper but warped and rippled, arching across the southern celestial sphere. Some regions are dense superclusters, bustling metropolises of galaxies, while others thin out into sparse filaments, cosmic countryside between urban hubs. This unevenness offers a treasure trove of clues about how dark matter, the universe's hidden scaffolding, shapes these vast formations. But here's the real twist. The sheer act of finding the South Pole Wall has opened doors to even grander possibilities. If something this massive could hide in our cosmic backyard, what else might be lurking just out of sight? Future telescopes, like the European Space Agency's Euclid mission, will peer deeper into these obscured zones, hunting for more hidden giants. The lesson is clear: the universe's grandest structures might not just be far away. They could be right behind us, waiting for the right tools to bring them into the light. For all the mind-bending structures we've explored so far, none hits closer to home than the Laniakea supercluster, the galactic metropolis we actually live in. Spanning 520 million light-years and containing over 100,000 galaxies, this vast cosmic watershed redefined our understanding of home when discovered in 2014. Picture a spiderweb glistening with dew, where each droplet isn't just a galaxy but an entire galaxy cluster, all flowing toward a hidden gravitational focal point like rivers merging into an invisible sea. What makes Laniakea Hawaiian for immeasurable heaven so revolutionary isn't just its scale, but how it was discovered. Traditional mapping focused on galaxies' positions, but astronomers led by R. Brent Tully at the University of Hawaii took a radically different approach, tracking motion. By measuring how galaxies drift through space like leaves on a slow-moving river, they uncovered a hidden pattern. All galaxies in our local universe, including the Milky Way, are being pulled toward a mysterious region called the Great Attractor, a gravitational focal point hidden behind the dust of our own galaxy's plane. These collective flows revealed Laniakea's true borders, showing we're part of something far grander than we imagined. Visualizing this supercluster feels like zooming out on a cosmic map for the first time. Our Milky Way resides on the outskirts of a filament called the local sheet, which itself is just one tendril flowing into the Virgo cluster, Laniakea's bustling downtown. From there, filaments of galaxies stretch outward like spokes on a wheel, all directed by the supercluster's gravitational currents. It's humbling to realize that even as we orbit the Sun, and the Sun orbits the galaxy, our entire galaxy is caught in this slow, inevitable drift toward the Great Attractor, traveling at 600 kilometers per second toward something we still don't fully understand. But here's what truly twists the mind. Laniakea might not even be the top of the cosmic hierarchy. Some studies suggest it could be part of an even larger structure, a ripple in an unfathomably vast arrangement we're only beginning to trace. And unlike distant walls or arcs, this isn't some far-off spectacle. It's our neighborhood, the streets and sidewalks of our cosmic address. Every star you see at night, every galaxy visible through a backyard telescope, all belong to this immense flowing network. The discovery didn't just expand our maps, it reshaped our place in the universe, proving that home isn't just a pale blue dot. It's a single thread in a tapestry larger than we ever dreamed. Just as we begin to grasp the sheer scale of Laniakea, the cosmos reveals an even grander truth. Our supercluster is merely one neighborhood within something far more immense. Welcome to the Pisces-Cetus supercluster complex, a sprawling cosmic continent stretching over 1 billion light-years. so vast that it contains not just Laniakea, but at least 3 other superclusters, all woven together like threads in a titanic tapestry. This isn't just a larger structure, it's a glimpse into the universe's deepest architectural blueprints, where gravity has sculpted matter into a network of staggering proportions. The discovery of this complex reshaped our understanding of cosmic geography. Imagine standing in a valley, realizing the mountains around you are just foothills of an entire mountain range. That's the leap in perspective Pisces Cetus demands. Named for the constellations where its densest regions lie, this megastructure was pieced together by mapping the gravitational ties between superclusters. Unlike the sharp edges of galaxy walls, its boundaries blur like a sprawling metropolitan area merging with suburbs, making it harder to define but no less real. What's truly staggering is how this complex defies the expected limits of cosmic growth. According to standard models, gravity needs time to pull matter into structures this colossal, more time than the universe's age should allow. Yet Pisces Cetus exists, suggesting either our models are incomplete or the early universe seeded these formations with mysterious density variations. Some theorists propose that dark matter's invisible web might have accelerated the process, while others speculate about primordial quantum fluctuations frozen into the fabric of space itself. Zooming out to see the full scale of Pisces Cetus is like watching a fractal reveal its layers. Within it, superclusters like Laniakea act as dense nodes, connected by faint filaments of galaxies' cosmic highways along which matter slowly drifts. The space between these filaments isn't empty. It's a dynamic medium where dark energy and gravity vie for dominance, stretching and compressing the structure even as we observe it. And here's the humbling twist. This billion-light-year Leviathan might still be just one piece of something larger. As telescopes peer deeper into space, each new map hints at scales we're only beginning to fathom. Pisces Cetus isn't just a destination in our cosmic exploration. It's a signpost pointing toward mysteries we've yet to uncover, reminding us that the universe's grandeur always outstrips our imagination. At the edge of the observable universe, where light has traveled nearly 13 billion years to reach us, lies a structure so immense it defies logic: the Huge Large Quasar Group, or Huge LQG. This staggering assembly of 73 quasars stretches 4 billion light-years across, forming a pattern so vast it would take a beam of light 4 times longer than Earth's entire existence just to traverse it. But what makes this discovery truly revolutionary isn't just its size, it's the fact that we're seeing it as it existed when the universe was barely 2 billion years old, a cosmic toddler by universal standards. Quasars aren't just ordinary galaxies, they're the blazing cores of active galactic nuclei, powered by supermassive black holes devouring unimaginable amounts of matter. Spotting one is rare. Finding 73 clustered together in a structured group this early in cosmic history sent shockwaves through astronomy. Imagine discovering a bustling modern city in what should be the Stone Age. That's the level of anomaly we're dealing with. According to standard models, the universe simply hadn't had enough time for gravity to pull matter into concentrations this massive so soon after the Big Bang. The huge LQG's discovery in 2013 forced scientists to confront a glaring question. How could such an enormous structure form when the cosmos was still in its infancy? One theory suggests these quasars trace the skeleton of a primordial supercluster, their black holes feasting on dense gas flows along dark matter filaments. Another radical idea proposes that what we're seeing isn't a true physical structure but a chance alignment like spotting faces in clouds. Though statistical analyses make this possibility vanishingly slim. What's truly mind-bending is how this formation challenges the cosmological principle at extreme distances. If the universe was truly uniform in its youth, concentrations of matter this dense shouldn't exist in such young cosmic epochs. Some researchers speculate that exotic physics, like variations in dark energy density or even flaws in Einstein's gravity theory, might explain this cosmic outlier. Others suggest we're seeing the fingerprints of quantum fluctuations from the universe's first moments, stretched to unimaginable scales by inflation. Mapping the huge LQG required piecing together observations from multiple telescopes, each capturing snapshots of different quasars across this titanic volume. Like reconstructing a continent from scattered islands, astronomers connected these blazing beacons to reveal the underlying structure. Yet even now, we're only seeing the brightest members. What lies between them, the galaxies and dark matter that must fill this colossal volume, remains hidden in the shadows of time. This discovery does more than add another record-breaking structure to our cosmic maps. It forces us to question whether our universe's largest features might have grown faster or formed differently than we ever thought possible. As telescopes like the James Webb peer deeper into these ancient epochs, each observation brings us closer to answering whether the huge LQG is a cosmic fluke or a sign that the early universe played by rules we're only beginning to decipher. While galaxies like our Milky Way appear vast to us, some single galaxies defy all expectations, stretching not just hundreds of thousands but millions of light years into space. These are the giant radio galaxies, cosmic anomalies where a single galaxy becomes the engine behind structures so enormous they dwarf entire galaxy clusters. What makes them truly mind-bending isn't just their size, it's that these titanic formations are born from something invisible, the furious energy of a supermassive black hole. At the heart of every giant radio galaxy lies an active galactic nucleus, where a black hole millions or even billions of times the sun's mass gorges on surrounding gas and dust. But unlike quieter black holes like Sagittarius in our Milky Way, these monsters don't just consume, they erupt. As matter spirals inward, some gets channeled into jets of charged particles shot outward at nearly light speed. These jets punch through intergalactic space for millions of years, carving out colossal lobes of radio-emitting plasma on either side of the host galaxy. Picture blowing up a balloon, but instead of rubber, it's made of magnetized gas stretching farther than the distance between the Milky Way and Andromeda, 16 million light-years in some cases. The lobes themselves are ghostly thin, like vast soap bubbles barely denser than the space around them. Yet their energy is staggering, enough to light up entire galaxies if converted into starlight. Telescopes like the Very Large Array in New Mexico see these structures not in visible light but in radio waves, revealing delicate filamentary patterns within the lobes. Some resemble the ripples of a pond disturbed by a stone, tracing shock waves from ancient outbursts of the central black hole. Others stretch asymmetrically, hinting at collisions with intergalactic gas clouds or the tug of neighboring galaxy clusters. What's even more fascinating is how these giants evolve. Unlike walls or filaments of galaxies shaped by gravity, giant radio galaxies are transient. Their lobes expand until they fade into the background over hundreds of millions of years, leaving only faint echoes of their existence. The longest known example, Alcyonius, stretches 5 megaparsecs, a fossil of a black hole's fury frozen in time. Yet even as one set of lobes dissipates, fresh eruptions can create new ones, layering the galaxy's history like rings in a tree. These cosmic megastructures force us to rethink how energy flows through the universe. They're proof that black holes aren't just destructive, they're architects, capable of sculpting space on scales we're only beginning to measure. And with every new radio telescope brought online, we find more of these giants lurking in plain sight, reminding us that even single galaxies can hold surprises vast enough to rewrite the rules of cosmic proportion. Long before the universe's great walls and superclusters took shape, the seeds of these colossal structures were already sprouting in the form of protoclusters, swarming nurseries of young galaxies that would one day grow into the densest hubs of the cosmic web. These primordial gatherings, some spanning over 60 million light-years, offer us a rare glimpse into how the largest arrangements in existence first began assembling, like watching a bustling metropolis emerge from scattered villages. What makes protoclusters extraordinary isn't just their size, it's their age. We're seeing them as they existed when the universe was less than 3 billion years old, a mere fraction of its current age. Unlike modern galaxy clusters, which are tightly bound cities of hundreds or even thousands of galaxies, protoclusters are still under construction. Picture a busy construction site where skyscrapers are only half built, with cranes and scaffolding everywhere. That's the chaotic, vibrant state of these ancient galactic gatherings. The discovery of these infant megastructures came from peering deep into the universe's past using telescopes like Hubble and ALMA. By capturing light that's traveled over 10 billion years to reach us, astronomers spotted dense knots of galaxies swimming in vast clouds of gas, drawn together by gravity's slow but unstoppable pull. One of the most famous examples, the SPD 2034-7 protocluster, contains a sprawling family of galaxies so active they're birthing stars at rates hundreds of times faster than our Milky Way today. The sheer energy output from these young galaxies is staggering enough to ionize the surrounding gas, carving out bubbles in the cosmic fog like lighthouses piercing through a dark sea. But how does something as vast as Laniakea or the Hercules-Corona Borealis Great Wall grow from these beginnings? The answer lies in the dark matter scaffolding that underpins all large-scale structure. Protoclusters form where dark matter's invisible tendrils are densest, funneling gas and galaxies into gravitational wells over billions of years. As galaxies within a protocluster collide and merge, their collective gravity pulls in more neighbors, snowballing into the superclusters we see today. It's a cosmic version of compound interest, where small early advantages in density lead to overwhelming accumulations of matter over time. What's truly mind-bending is that many protoclusters we observe may now be fully formed, collapsed into mature clusters, but we can't see their present state because their light hasn't reached us yet. In a sense, we're looking at cosmic baby pictures of titans now grown old, scattered across a universe that's been expanding all this time. Future telescopes like the James Webb Space Telescope will peer even further back, hunting for protoclusters in their earliest stages, perhaps even catching the moment when the first strands of the cosmic web began weaving together. These primordial gatherings don't just teach us about the past, they reveal the future. By studying protoclusters, we're watching the universe's largest structures take their first breaths, a slow-motion spectacle of cosmic architecture unfolding across billions of years. And with each new discovery, we come closer to answering one of astronomy's deepest questions. How does a perfectly smooth early universe transform into the intricate, web-like cosmos we inhabit today? The protoclusters hold the clues written in starlight older than Earth itself. Even as we map the universe's largest structures, walls of galaxies, voids, and superclusters, an even stranger mystery tugs at the edges of our understanding. Imagine every galaxy cluster in the observable cosmos, thousands of them, all drifting in the same direction at inexplicable speeds, as if pulled by an unseen hand. This isn't science fiction, it's the baffling phenomenon known as the dark flow, a discovery so unsettling it hints at forces beyond the limits of everything we can see. The story begins with galaxy clusters, the universe's heaviest objects, each containing thousands of galaxies bound by gravity. Normally, their motion should be random, like leaves scattered by wind. But in 2008, astronomers analyzing data from NAS, a Wilkinson microwave anisotropy probe, stumbled onto something impossible. Hundreds of these clusters were moving en masse toward a single patch of sky near the constellations Centaurus and Hydra, some at speeds exceeding 600 kilometers per second. It wasn't just a few outliers, it was a coordinated rush of matter on a scale no known force could explain. What could possibly exert such a pull? One radical theory suggests the dark flow is the gravitational tug of something outside our observable universe, perhaps a supermassive structure lurking in the uncharted regions beyond cosmic inflation's horizon. If true, it would mean our universe isn't just vast, it's part of something even grander, a multiversal landscape where our cosmic bubble brushes against others. Another idea points to flaws in our understanding of gravity itself, proposing that Einstein's equations break down at the largest scales, yet skeptics argue the dark flow might be an illusion. Some suggest uneven heating in the early universe could mimic the effect, while others question whether the data's statistical significance holds. The debate grew fiercer when later studies using the Planck satellite failed to confirm the original findings, leaving the phenomenon in scientific limbo, neither proven nor dismissed. The implications haunt cosmologists. If the dark flow is real, it challenges the cosmological principle, the bedrock idea that the universe is uniform in all directions. How do you map what you can't see? How do you measure forces from beyond the edge of existence? Future missions like the European Space Agency's Euclid telescope may finally settle the debate, but for now, the dark flow remains one of astronomy's most tantalizing enigmas, a ghostly current in the cosmic ocean, hinting at depths we've yet to explore. Among the subtle ripples and temperature variations of the cosmic microwave background, the afterglow of the Big Bang itself, there's one anomaly so bizarre it stands out like a cosmic bruise. Known as the cold spot, this circular region spans a staggering 1.8 billion light-years and registers colder than its surroundings by about 70 microkelvins. That might sound negligible, but in the ultra-precise world of cosmology, it's like finding a patch of ice in the Sahara. This isn't just unusual, it's statistically improbable, a fluke so extreme that some scientists wonder if it's whispering secrets about realms beyond our own. What makes the cold spot truly fascinating is the battle to explain it. The leading theory suggests it's a supervoid, an enormous, mostly empty region of space where matter is so sparse that light passing through loses energy, creating a chilling effect in the microwave background. Picture a photon traveling through this void like a cyclist pedaling uphill. It expends energy fighting gravity's weakened but persistent pull, arriving at our telescopes slightly colder and wearier than light from denser regions. Supervoids exist elsewhere in the cosmos, but none match the cold spot's sheer scale. If confirmed, this would be the largest known void in existence, a cosmic desert so vast it could swallow entire superclusters without a trace. Yet there's a problem. Detailed galaxy surveys like those from the Anglo-Australian telescope reveal the cold spot's underdensity isn't quite extreme enough to fully explain the temperature drop. The math leaves a gap, like finding a puddle too large for the rain cloud overhead. This discrepancy has fueled a radical alternative. The cold spot might be evidence of a collision with another universe. In certain multiverse theories, our cosmos could be one bubble among many in a frothy multiverse. If a neighboring bubble universe brushed against ours long ago, the energy released might have left a thermal fingerprint, an imprint cooler than its surroundings. It's a speculative idea, but one that turns the cold spot from a curiosity into a potential window onto existence beyond our cosmic horizon. Debate still rages. Some researchers argue the cold spot is a statistical illusion, a random fluctuation magnified by our human tendency to find patterns. Others propose exotic physics like primordial magnetic fields or dark energy's quirks as culprits. The Planck satellite's meticulous maps added fuel to the fire, confirming the anomaly's existence but leaving its origin unresolved. What's undeniable is the cold spot's power to challenge assumptions. If it's a supervoid, it stretches our models of cosmic structure. If it's a multiverse signature, it rewrites our place in reality. Future telescopes, like the Simons Observatory in Chile, will scrutinize this region with unprecedented precision. But for now, the cold spot lingers as one of cosmology's greatest riddles, a cryptic mark on the universe's oldest light, daring us to unravel its secrets. Whether a void or a cosmic scar, it reminds us that even 13.8 billion years after the Big Bang, the universe still holds mysteries cold enough to give scientists chills. We might think of our Milky Way as nestled in a bustling galactic neighborhood, but the truth is far stranger. We're floating in one of the universe's emptiest regions, the KBC Void. Named after astronomers Keenan, Barger, and Cowie, who identified it in 2013, this staggering sphere of near-nothingness stretches 2 billion light-years across, making it the largest known void in our cosmic vicinity. To grasp the sheer emptiness, imagine standing in the middle of a desert so vast you'd need to walk for lifetimes just to reach the edge. Only this desert isn't sand, but an expanse where galaxies are so sparse, our night sky appears unnaturally dark compared to denser regions of the cosmos. What makes the KBC Void extraordinary isn't just its size. It's how it warps our view of the universe, because we're inside it. Looking outward is like peering from the bottom of a well. The surrounding walls of galaxies appear brighter and more densely packed than they truly are, creating an illusion that we're at the center of a cosmic amphitheater. Early astronomers fell for this trick, assuming the Milky Way occupied a special place in the cosmos. Now we know better. We're simply residents of a quiet backwater, a galactic countryside where the nearest major superclusters, like Laniakea, loom on the distant shores of this void. Living here has profound scientific consequences. The vacuum around us means nearby galaxies are fewer and farther between, making it harder to study cosmic evolution up close. It also affects how we measure the universe's expansion. In denser regions, gravity's pull slows the stretching of space, while in voids like ours, dark energy's repulsive force dominates, accelerating the void's growth like a celestial souffle. This imbalance skews our local measurements of Hubble's constant, the rate of cosmic expansion, leading to heated debates among cosmologists about the true value. Yet the KBC Void isn't entirely empty. It's dotted with field galaxies, lonely wanderers like our own Milky Way, drifting through the cosmic wilderness. Some may be refugees ejected from clusters by gravitational slingshots, while others could be the last remnants of faint filaments too dim to detect. Their isolation makes them cosmic time capsules, preserving clues about how galaxies evolve when untouched by the violent collisions common in denser regions. The void's existence also hints at a deeper truth. The universe's structure is fractal-like, with smaller voids nested inside larger ones. The KBC Void might be just one bubble in a froth of emptiness stretching across the cosmos. And here's the humbling twist. If we could teleport to a galaxy in a supercluster like Coma, our night sky would blaze with thousands of visible galaxies, a spectacle so dazzling it would make our current view seem like a lonely outpost. Far from being a cosmic quirk, the KBC Void reshapes our understanding of place. It's a reminder that the universe doesn't center around us, and that even emptiness holds secrets about dark energy, galactic evolution, and the fate of everything. As telescopes map deeper into space, each new void discovered peels back another layer, revealing just how much we've yet to learn about the grand, interconnected web we call home. Somewhere beyond the stars, hidden behind the dense curtain of our own Milky Way, an invisible force tugs at the fabric of the cosmos, the Great Attractor. This mysterious gravitational powerhouse pulls thousands of galaxies, including our own, toward it at speeds exceeding 600 kilometers per second. It's as if the universe has a hidden whirlpool, and everything in our galactic neighborhood is caught in its current, drifting toward a point we can't even see clearly. What makes this phenomenon so baffling is its location. It lies in the so-called zone of avoidance, an area of the sky obscured by the Milky Way's dust and stars. Traditional telescopes can barely penetrate this region, leaving astronomers to piece together clues using radio and infrared observations that cut through the cosmic fog. Early maps revealed something massive was there, roughly 400 million light-years away, with the gravitational heft of tens of thousands of Milky Ways combined. But what exactly is it? The leading theory suggests the Great Attractor isn't a single object but a dense knot of galaxies known as the Norma Cluster, embedded within the larger Laniakea supercluster. Picture a bustling city at the intersection of cosmic highways, where filaments of dark matter funnel galaxies together into a gravitational hotspot. Yet even this colossal cluster doesn't fully account for the observed pull, hinting that something even larger, perhaps an unseen supercluster, lurks behind it, amplifying its influence. Some researchers propose an even wilder idea. The Great Attractor might be just the visible tip of a far grander flow, part of a vast river of galaxies being pulled towards something even more distant. This could explain why galaxies farther out, like those in the Puppies and Hydra clusters, also seem to move in sync with the pull. It's like standing in a valley and sensing a breeze, only to realize the wind isn't local but part of a storm system spanning the horizon. Efforts to unravel this mystery have led to astonishing discoveries. X-ray telescopes like Chandra revealed hot gas clouds swirling around the Norma cluster, evidence of violent collisions between galaxies. Meanwhile, surveys like the Cosmic Flows Project mapped the motion of thousands of galaxies, tracing the invisible tendrils of gravity shaping our corner of the universe. Each new dataset peels back another layer, but the Great Attractor remains elusive, its true nature still veiled by the Milky Way's glare. One thing is certain, this invisible titan reshapes our understanding of cosmic motion. It reminds us that even in a universe of unfathomable scale, local forces can orchestrate grand movements, drawing entire galaxies into an unseen dance. And as next-generation telescopes probe deeper into the zone of avoidance, we inch closer to answering the question that's haunted astronomers for decades. What lies in the darkness, pulling us toward it with irresistible cosmic hands? If the Great Attractor is the mysterious force pulling our galactic neighborhood, then the Shapley supercluster is the heavyweight champion. It's dragging us toward a gravitational behemoth so massive it redefines what we thought possible for cosmic structure. Located 650 million light-years away in the constellation Centaurus, this sprawling metropolis of galaxies isn't just big, it's the single largest concentration of matter in our observable cosmic backyard. A gravitational anchor so powerful it bends the very flow of the universe around it. Picture a cosmic New York City, but instead of skyscrapers, imagine galaxy clusters, each one a dense hive of thousands of galaxies packed so tightly they blur into a single shimmering mass. The Shapley supercluster contains at least 25 major clusters and dozens of smaller groups, all bound together by dark matter's invisible threads. Its total mass, roughly 10,000 Milky Ways combined. That's enough gravitational pull to slow the expansion of space itself in its vicinity, creating a counter-current to dark energy's relentless push. What makes Shapley truly extraordinary is its role in the cosmic tug-of-war we're caught in. While the Great Attractor explains part of our local motion, studies reveal Shapley's gravity is the dominant force pulling not just us, but entire superclusters toward it. Think of it like a hidden mountain range whose peaks warp the winds for thousands of miles, except here, the winds are galaxies and the mountain is a gravitational titan shaping the flow of the local universe. Mapping this giant wasn't easy. Unlike the striking walls or voids we've explored, Shapley's structure is messy, its clusters overlapping and blending in a tangle of gravity and light. Astronomers had to combine X-ray observations which reveal the searing hot gas between galaxies with redshift surveys to untangle its true scale. The result? A revelation that Shapley isn't just a random pile-up of clusters but the dense core of an even larger filament, a nexus where multiple strands of the cosmic web converge like rivers merging into a delta. Yet Shapley holds a cosmic irony. Despite its staggering scale, it's virtually invisible to the naked eye. From Earth, its region of the sky looks unremarkable, a quiet patch of stars hiding the universe's most crowded zip code. Even its discovery was accidental. Astronomer Harlow Shapley stumbled upon its brightest clusters in the 1930s while studying nearby galaxies, unaware he'd glimpsed the edge of something far grander. Now, here's what really twists the mind. Shapley's existence challenges our models of cosmic evolution. How did so much matter pile up in one place so quickly? Simulations suggest it might be a rare overdensity, a fluke of the early universe where extra dark matter pooled like cream rising to the top. Others propose it's the result of a cosmic traffic jam, where multiple filaments collided over billions of years, compressing galaxies into this staggering superstructure. As telescopes like Euclid and the Vera Rubin Observatory turn their gaze toward Shapley, they'll probe deeper into its secrets, how it influences galaxy evolution, whether it houses unknown dark matter quirks, and if it's truly the end of our gravitational journey or just a waypoint to something even larger. For now, it stands as a humbling reminder. Even in a universe of unfathomable scale, some structures loom so large they pull not just galaxies, but the course of scientific discovery itself. Buried within the vast cosmic web, hidden among the universe's grandest structures, lies a wall so immense it could hold 1 trillion Milky Ways, the Great Wall. Discovered in 2016 through the Baryon Oscillation Spectroscopic Survey, this staggering filament of galaxies stretches an almost unimaginable 1 billion light-years across, a labyrinth of superclusters woven together by dark matter's invisible threads. But what makes this colossus truly groundbreaking isn't just its size. It's how it acts as a cosmic yardstick, allowing us to measure dark energy's relentless push against gravity's grip. BOSS didn't just stumble upon this titan by accident. Scientists designed the survey specifically to hunt for baryon acoustic oscillations, frozen ripples in the universe's matter left over from the Big Bang's primordial soup. Picture throwing a stone into a pond. The ripples spread outward, then freeze in place as the universe cools. These ripples, now stretched to 500 million light-years apart, serve as a natural ruler etched into the cosmos. By mapping the positions of over 1.2 million galaxies, BOSS revealed something astonishing. Galaxies weren't scattered randomly but clustered along these ancient echo patterns, forming the spine of the Great Wall. Here's where dark energy enters the story. As the universe expands, dark energy's repulsive force fights gravity's pull, subtly altering the spacing between these baryon oscillations. The Wall's sheer scale makes it a perfect laboratory. Its vastness means even tiny shifts in these cosmic rulers reveal dark energy's fingerprints. Think of it like measuring a rubber band as it stretches. The longer it gets, the easier it is to spot if someone's tugging at one end. By studying how the wall's galaxies are distributed compared to the expected oscillation scale, astronomers confirmed dark energy's acceleration isn't just real. It's winning the cosmic tug-of-war, stretching space faster than gravity can clump matter together. But the Wall isn't just a tool for measuring dark energy, it's a puzzle in its own right. Like the Sloan Great Wall, its existence pushes the limits of how quickly cosmic structures can grow. Its dense knots of galaxies, strung along filaments like pearls on a necklace, shouldn't have had time to assemble so coherently under standard models. Some theorists suggest quirks in dark matter's behavior might explain it, while others wonder if dark energy's properties vary across space, warping growth rates in unexpected ways. What's next? Upcoming surveys like Daisy and Euclid will map even more galaxies, probing fainter and farther to see if the Wall connects to even larger structures. Every new data point peels back another layer of this cosmic onion, revealing how dark energy, dark matter, and gravity dance together across the universe's grandest stages. And as we stare deeper into these maps, one haunting question lingers. If this is what we've found so far, what other titans lie waiting in the uncharted darkness? While most of the universe's largest structures emerged over billions of years, some colossal formations defy expectations by appearing far earlier than they should, like the Saraswati supercluster, a sprawling cosmic metropolis glimpsed when the universe was barely half its current age. Discovered in 2017 by Indian astronomers combing through data from the Sloan Digital Sky Survey, this gargantuan structure spans 600 million light-years, comparable to the width of 8,000 Milky Ways placed end to end. But what sets Saraswati apart isn't just its staggering scale. It's the fact we're seeing it as it existed 4 billion years after the Big Bang, a cosmic toddler by universal standards, yet already boasting the maturity of structures 10 times older. The Saraswati supercluster resembles an enormous spiderweb woven from 42 massive galaxy clusters, each containing hundreds or even thousands of galaxies. Imagine New York City's skyline multiplied across intergalactic distances, with towering cluster cores acting like downtown hubs connected by highways of galaxies. What's breathtaking is how quickly this megastructure assembled. According to conventional models, gravity needed at least 8 to 10 billion years to sculpt matter into such coherent formations. Saraswati's existence suggests something supercharged this process, perhaps denser than average dark matter scaffolding or quirks in the early universe's expansion that gave gravity a head start. Mapping this ancient giant required piecing together clues from multiple wavelengths. Optical telescopes captured the glow of its galaxies, while X-ray observatories like Chandra revealed the superheated gas trapped between them, evidence of violent collisions as clusters merged. But the real revelation came from studying galaxy motions. Unlike younger superclusters still settling into shape, Saraswati's members orbit with eerie coordination, like bees in a hive, signaling it had already reached a stable, mature configuration astonishingly early. This precocious maturity throws a wrench into cosmic evolution theories. Most simulations struggle to grow structures this massive so quickly without invoking exotic physics, maybe primordial dark matter, clumpiness, or bizarre early-state energy fields. Some researchers speculate Saraswati might be the core of an even larger, still hidden structure, its true boundaries lost in the observational noise of intervening dust and stars. Others propose it's a rare cosmic fluke, a statistical outlier in an otherwise uniform early universe. Yet Saraswati's greatest gift isn't the mystery, it's the perspective. By studying superclusters this ancient, we witness the universe's adolescence, a time when dark energy's influence was weaker and gravity still dominated cosmic construction. Future telescopes like the 30-meter telescope will probe even earlier epochs, hunting for infant Saraswatis that could rewrite our timeline of cosmic growth. For now, this titanic relic stands as both a triumph and a challenge, proof that the universe's architectural genius began crafting marvels far sooner and far grander than we ever imagined possible. At the edge of our observational limits, where light has traveled nearly 12 billion years to reach us, floats a cosmic blueprint for all future superclusters, the Hyperion proto-supercluster. This primordial giant, spotted when the universe was a mere 2 billion years old, shouldn't exist according to conventional models, yet there it sprawls, a sprawling metropolis of galaxies 5,000 times more massive than the Milky Way, already taking shape when the cosmos was in its infancy. Hyperion isn't just old, it's shockingly well developed. Unlike later superclusters that formed gradually, this ancient megastructure appeared fully framed, its galaxies already woven into an intricate web by dark matter's invisible hands. Picture finding the ruins of a skyscraper in Stone Age archaeology. That's the level of cosmic precocity we're dealing with. Discovered in 2018 by the Very Large Telescope's groundbreaking observations, Hyperion's 10,000 galaxies cluster into at least 7 dense filaments, each stretching hundreds of millions of light-years, converging like rivers feeding a colossal lake. What makes this discovery revolutionary is the timeline. Standard simulations suggest dark matter needed at least 6 billion years to sculpt matter into such coherent structures. Hyperion's existence implies that the early universe wasn't the smooth, evenly distributed soup we imagined. It must have had denser lumps that jump-started gravitational collapse. Some astronomers speculate it formed at a rare intersection of primordial sound waves from the Big Bang, while others wonder if dark matter behaved differently in the universe's hotter, denser youth. Peering into Hyperion is like watching time-lapse footage of cosmic construction. Gas-rich galaxies within it birth stars at rates 100 times faster than modern galaxies, their collisions igniting fireworks of stellar formation. X-ray telescopes detect halos of searing plasma, evidence of violent mergers heating intergalactic gas to millions of degrees. Yet amid this chaos, the supercluster's backbone remains eerily organized, its dark matter scaffold already outlining the cosmic web we recognize today. The implications ripple across cosmology. If structures as vast as Hyperion could form so early, our entire understanding of galaxy evolution might need recalibrating. Future observatories like the James Webb Space Telescope will hunt for even older protoclusters, probing whether Hyperion was a cosmic fluke or the first glimpse of a universe that built its grandest designs on a schedule we're only beginning to decipher. For now, this ancient titan stands as both a marvel and a mystery, a reminder that the universe's architectural genius was at work long before we thought possible. Among the universe's most puzzling structures, none bends the mind quite like the giant Giabi ring, a near-perfect circle of gamma-ray bursts spanning 5.6 billion light-years, so vast it would take light more than twice the age of our solar system just to cross from one side to the other. Discovered in 2015 by astronomers analyzing data from the Swift and Fermi gamma-ray telescopes, this colossal formation isn't just enormous, it's hauntingly symmetrical, a cosmic bull's-eye etched into the fabric of space with precision that defies easy explanation. Gamma-ray bursts, the universe's most violent explosions, typically scatter randomly across the sky. But when researchers mapped 9 particularly luminous bursts, they formed a ring so geometrically striking it couldn't be coincidence. Picture tossing pebbles into a pond and watching them land in a flawless circle. That's the statistical improbability astronomers faced. The ring's diameter stretches roughly 1/11th of the observable universe, making it the largest regular structure ever detected. Yet its origins remain shrouded in mystery, challenging our deepest assumptions about how matter organizes itself across cosmic scales. What could possibly create such a formation? One leading theory suggests the ring traces the edges of a spherical shockwave from the early universe, frozen in time like a fossilized bubble. In the cosmos' first moments, quantum fluctuations might have triggered titanic collisions between space-time regions, sending ripples through the infant universe that later seeded galaxy formation along their crests. Another radical idea proposes the ring is a cosmic string imprint, a hypothetical defect in spacetime's fabric left over from the Big Bang, where unimaginably dense threads of energy warped surrounding matter into this eerie symmetry. Yet the giant Giabi ring's existence isn't just a curiosity, it's a potential crisis for cosmology. The cosmological principle, which states the universe should look roughly uniform at large scales, struggles to accommodate such a colossal, ordered structure. If matter can clump into rings of this scale, our models of cosmic evolution might need rewiring. Some researchers argue the ring could be a projection effect, an illusion created by galaxies aligning along our line of sight. But follow-up studies suggest the structure's three-dimensionality is real, its bursts distributed across mind-bending distances rather than flattened into a screen. Mapping this titan required ingenuity. Gamma-ray bursts, though fleeting, act like cosmic lighthouses, their positions revealing hidden concentrations of matter. By correlating bursts with galaxy surveys, astronomers traced the ring's outline against the darkness, a circle so large it covers the width of 60 full moons in our night sky. But here's the twist: we're not seeing the ring as it exists today. The burst's light has traveled for billions of years, meaning the structure we observe is a fossil from when the universe was half its current age. Whether it still persists, stretched and distorted by cosmic expansion, remains unknown. The giant GRB ring stands as both a marvel and a provocation, a whisper from the depths of time that challenges us to rethink the universe's architecture. Future telescopes like the Cherenkov Telescope Array may detect more such formations, revealing whether this ring is a cosmic rarity or one thread in a hidden tapestry of colossal patterns. Until then, it remains a humbling reminder: even after millennia of stargazing, the universe still knows how to surprise us with geometries grander than our boldest imaginations. Deep within the cosmic microwave background, the faint glow of the Big Bang's afterglow, there's a chilling anomaly that has puzzled astronomers for decades: the cold spot. This eerie patch in the constellation Eridanus is noticeably colder than its surroundings by about 70 microkelvins, a discrepancy that seems minor until you realize it spans nearly 1.8 billion light-years. What could possibly create such a vast, frosty imprint on the universe's oldest light? The leading suspect is one of the most colossal voids ever proposed: the Eridanus supervoid, a cosmic desert so staggeringly empty it might just be the universe's largest shadow. Unlike the Boots void, which still hosts a smattering of lonely galaxies, the Eridanus supervoid appears almost barren, a region where matter is so sparse it forms a near-perfect vacuum on scales that defy comprehension. Picture a bubble blown into the fabric of space, stretching wider than the distance between Earth and the most distant quasars, yet containing almost nothing inside. When light from the cosmic microwave background passes through this void, it loses energy in a process called the integrated Sachs-Wolf effect. Think of a cyclist coasting uphill. Photons struggling against the void's weakened but persistent gravitational pull arrive at our telescopes slightly colder and wearier than those from denser regions. But here's where the mystery deepens. The Eridanus supervoid's sheer size should make its imprint on the CMB far more dramatic than what's observed. Detailed galaxy surveys suggest the void's underdensity, the degree to which it's emptier than average, isn't extreme enough to fully explain the cold spot's temperature drop. It's like finding a footprint in the snow that's too large for any known animal. This gap has sparked wilder theories. Could the cold spot be evidence of a collision with a parallel universe? Some models of the multiverse suggest that if our cosmos bumped against another bubble universe, the energy released might leave a thermal bruise, an imprint cooler than its surroundings. Yet skeptics argue the supervoid might not even exist. Alternative explanations range from primordial magnetic fields imprinting patterns on the early universe to statistical flukes amplified by our human tendency to find meaning in randomness. The Planck satellite's meticulous maps confirmed the cold spot's reality, but left its origins unresolved, leaving astronomers torn between two equally radical possibilities: an unfathomably vast emptiness or a crack in the foundations of cosmology itself. What's undeniable is the cold spot's power to humble our understanding. Whether a void or a cosmic scar, it forces us to confront how little we grasp about the universe's largest structures and the invisible forces that shape them. Future telescopes like the Simons Observatory will probe this enigmatic region with unprecedented precision. Until then, the cold spot lingers as a tantalizing riddle, a whisper from the depths of time that refuses to be ignored. Stretching across the southern skies like a cosmic tapestry woven from the threads of 300,000 galaxies, the Horologium Reticulum Supercluster stands as one of the most colossal and overlooked structures in our celestial neighborhood. Spanning 550 million light-years, this sprawling network of galaxies isn't just vast. It's a gravitational masterwork, binding together clusters and filaments into a single, interconnected web that rivals even the Great Laniakea in sheer scale. What makes it truly fascinating, though, isn't just its size, it's the story it tells about how the universe organizes matter in regions we're only beginning to map. Unlike the prominent northern superclusters visible from Earth's more populated hemispheres, Horologium Reticulum hides in relative obscurity, tucked beneath the Milky Way's dusty disk. Its discovery required peering through our galaxy's veil using infrared and radio telescopes, which revealed a sprawling metropolis of galaxies moving in concert, pulled by dark matter's unseen currents. Picture a bustling city seen through fog. Only this city is built from clusters like Abell 326 and Abell 301, each one a gravitational anchor for thousands of galaxies. The supercluster's spine, a sinuous filament of galaxies and gas, acts like a cosmic freeway, funneling matter toward dense nodes where clusters collide and merge in slow-motion fireworks. But here's what sets Horologium Reticulum apart: its peculiar motion. While most superclusters drift with the universe's expansion, this one seems to be swimming against the tide, tugged by something even larger lurking beyond our current maps. Astronomers call this the dipole repeller, a hypothetical region of such extreme emptiness that it effectively pushes nearby structures away like a cosmic vacuum. This strange dance between attraction and repulsion hints at forces shaping the universe's large-scale structure in ways we're only starting to grasp. Zooming into its heart reveals another marvel. The supercluster isn't just a random pile of galaxies. Its components are arranged in a hierarchy, with smaller groups orbiting larger clusters like planets around a star. Some of these galaxies are ancient, their stars forged barely a billion years after the Big Bang, while others are stellar nurseries, birthing new suns at rates that dwarf our Milky Way's quiet pace. This diversity offers a time capsule of cosmic evolution, showing how environments shape galaxies over billions of years. Yet for all its grandeur, Horologium Reticulum remains a frontier. Upcoming telescopes like the Vera Rubin Observatory will finally bring its faintest members into focus, mapping the full extent of its filaments and voids. What we've seen so far might just be the outline of something even grander, a single thread in a tapestry still being woven. And that's the humbling truth. Even structures of this scale are mere waypoints in a universe that always seems to have another layer of mystery waiting just beyond the edge of our vision. Behind the glowing band of the Milky Way, where our galaxy's dust and stars obscure nearly a quarter of the night sky, astronomers have uncovered a hidden leviathan, the Vela supercluster. This recently discovered behemoth, stretching 500 million light-years and containing at least 5 massive galaxy clusters, had lurked unseen until sophisticated radio surveys pierced the cosmic veil in 2016. Its discovery wasn't just a triumph of technology, it was a humbling reminder that some of the universe's grandest structures might be hiding in our own celestial backyard, camouflaged by the Milky Way's brilliance. What makes Vela extraordinary isn't just its scale, though it rivals the Shapley supercluster in sheer mass, but how it reshapes our understanding of local cosmic geography. Before its detection, astronomers assumed the Hydra Centaurus supercluster was the dominant mass in our intergalactic neighborhood. Vela's revelation turned that assumption on its head. Imagine thinking you've mapped all the continents on Earth, only to suddenly discover a new landmass the size of Asia obscured by ocean fog. That's the scale of recalibration this discovery demanded. Peering through the Milky Way's obstruction required ingenuity. Traditional optical telescopes couldn't penetrate the dense star fields, so scientists turned to radio waves and infrared light, which slice through dust like headlights cutting through fog. The Parkes Radio Telescope in Australia played a pivotal role, mapping hydrogen gas emissions to trace galaxy motions. When researchers analyzed these movements, they found thousands of galaxies flowing toward an unseen gravitational anchor, the telltale sign of a supercluster's pull. Follow-up observations with the Southern African Large Telescope confirmed the find, a titanic structure centered around the Vela constellation. its gravity orchestrating the motion of galaxies across a volume wider than 4,000 Milky Ways placed end to end. But Vela isn't just a passive collection of galaxies. Its core hosts violent mergers between galaxy clusters, where collisions heat gas to millions of degrees, creating X-ray glows detectable by space telescopes like Chandra. These chaotic interactions offer a preview of what our local group might experience billions of years from now as it spirals toward the Virgo cluster. Meanwhile, the supercluster's outer filaments act like cosmic highways, funneling galaxies toward denser regions in a slow-motion migration that's been underway since the universe was half its current age. Perhaps the most startling implication of Vela's discovery is what it suggests about the unseen cosmos. If something this massive could hide behind the Milky Way's disk, what other giants might be concealed just beyond our view? Upcoming surveys like the Square Kilometre Array will scan these obscured zones with unprecedented sensitivity, potentially rewriting our cosmic maps yet again. For now, the Vela supercluster stands as both a milestone and a mystery, a reminder that even in an age of advanced astronomy, the universe keeps its grandest designs partially veiled, waiting for the right tools to bring them into the light. Nestled within the intricate tapestry of the cosmic web, the Coma Wall stands as a titanic backbone of galaxies, a dense filament stretching over 500 million light-years, studded with some of the most massive clusters known to science. At its heart lies the legendary Coma Cluster, a bustling galactic metropolis containing over 1,000 galaxies bound together by gravity's unrelenting grip. What makes this wall extraordinary isn't just its scale, but how it reveals the invisible architecture of the universe, where dark matter's hidden scaffolding orchestrates the ballet of galaxies across unfathomable distances. Picture the Coma Wall as a celestial highway, its lanes traced by shimmering galaxies, all flowing toward the cluster's core like moths to a flame. The Coma Cluster itself acts as a gravitational anchor, its combined mass equivalent to 20,000 Milky Ways, warping spacetime so profoundly that even light bends around it. But the wall isn't just a straight line. It's a dynamic, twisting structure with tendrils branching outward like roots of a cosmic tree. These filaments funnel gas and galaxies into the cluster's maw, fueling violent collisions that heat intergalactic gas to millions of degrees, creating a glow visible in X-ray telescopes. Mapping this leviathan required decades of painstaking observation. Astronomers began by charting the Coma Cluster's galaxies in the 1930s, unaware they'd glimpsed the tip of something far grander. Later redshift surveys revealed the shocking truth. The cluster wasn't an island, but the brightest jewel in a necklace of galaxies spanning hundreds of millions of light-years. The wall's full dimensions only emerged when scientists mapped galaxies in 3 dimensions, exposing how they clustered along dark matter's invisible rivers. What makes the Coma Wall especially fascinating is its role in cosmic evolution. Unlike younger superclusters still settling into their shapes, this structure is nearly mature, a snapshot of what Laniakea might become billions of years from now. Its galaxies are mostly old and quiet, their star-forming gas long since stripped away by the cluster's brutal gravitational tides. Yet even here, surprises lurk. Deep within the wall's filaments, astronomers have found orphan galaxies, isolated wanderers that somehow avoided being swallowed by the cluster, preserving clues about the universe's early structure. Standing back to view the Coma Wall in context reveals an even grander truth. It's just one segment of the universe's vast skeleton. It connects to the Leo cluster, another massive node, forming part of a supercluster complex that might stretch beyond our current maps. Future telescopes like Euclid will probe these connections further, tracing how walls like Coma channel matter across the cosmos. For now, this galactic colossus serves as a reminder. The universe builds its grandest structures not in isolation, but as threads in an endless, interconnected web. Pushed to the far edges of the observable universe, where light takes 10 billion years to reach us, lies a time capsule of cosmic construction, the Lynx supercluster. This ancient metropolis of galaxies, observed as it existed when the universe was just a quarter of its current age, offers a rare glimpse into how the largest structures in existence first took shape. Unlike the mature superclusters we see nearby, Lynx isn't a polished cosmic city but a bustling construction site. Its galaxies caught in the frenzied act of assembly, revealing secrets about the universe's formative years. Discovered in the late 1990s by astronomers combing through redshift surveys, Lynx stands out even among distant superclusters. Its core contains two massive galaxy clusters, Lynx East and Lynx West, each already weighing as much as several hundred Milky Ways, yet separated by just 60 million light-years. Picture two skyscrapers rising side by side in a primordial metropolis, their gravitational pull drawing thousands of smaller galaxies into a sprawling web. What makes this structure revolutionary is its youth. Most superclusters this massive are seen much later in cosmic history, but Lynx defied expectations by achieving such scale and density while the universe was still in its adolescence. Peering into Lynx is like watching time-lapse footage of urban development. The Hubble Space Telescope's deep-field images reveal galaxies ablaze with star formation, their gas-rich disks colliding and igniting bursts of stellar birth at rates 100 times faster than our own Milky Way. X-ray observations detect halos of superheated plasma, evidence of violent mergers heating intergalactic gas to temperatures exceeding 10 million degrees. Yet amid this chaos, dark matter's invisible scaffolding is already at work, channeling galaxies into filaments that will one day solidify into the cosmic web's grand filaments. What's truly astonishing is how Lynx challenges our timeline of cosmic evolution. Standard models suggest superclusters this massive shouldn't have existed so early. Their existence hints that the early universe might have been lumpier than we thought, with denser patches of dark matter accelerating gravitational collapse. Some theorists propose these regions were seeded by primordial sound waves from the Big Bang ripples frozen into the fabric of space that later became the blueprints for galactic megastructures. Others wonder if dark matter's properties were subtly different in the hotter, denser early universe, clumping faster than our simulations predict. Lynx's most valuable gift, though, is perspective. By comparing it to younger superclusters like Shapley or Laniakea, astronomers trace how these cosmic titans evolve over time. In Lynx, galaxies are still falling into the clusters for the first time, their motions chaotic and uncoordinated. Billions of years later, this dance will settle into the stately orbits we see in mature clusters, where galaxies move like synchronized swimmers in a gravitational ballet. Yet for all we've learned, Lynx remains enigmatic. Current telescopes can only capture its brightest members, leaving the fainter threads of its web unresolved. The upcoming James Webb Space Telescope will peer deeper, uncovering dwarf galaxies and faint filaments that could rewrite our understanding of early cosmic structure. And that's the thrill of discoveries like this. They're not just answers, but invitations to ask new questions about how the universe builds its grandest designs and how much we've yet to uncover in the darkness beyond. Tucked away in the constellation of Ophiuchus, hidden behind the Milky Way's dense starfields, lies a cosmic titan that redefines our understanding of raw power, the Ophiuchus supercluster. This colossal assembly of galaxies, stretching over 300 million light-years, is anchored by one of the most massive galaxy clusters ever discovered, a gravitational powerhouse so immense it warps spacetime itself. But what truly sets this supercluster apart isn't just its scale, it's the record-breaking explosion that erupted from its heart, an outburst so cataclysmic it carved a crater in the surrounding gas large enough to swallow 15 Milky Ways side by side. At the core of this supercluster sits the Ophiuchus cluster, a maelstrom of galaxies swirling around a supermassive black hole with an appetite that defies belief. In 2020, astronomers analyzing X-ray data from NASA Chandra Observatory stumbled onto something extraordinary, a cavity in the hot gas surrounding the cluster so vast it spanned 1.5 million light-years. This wasn't just any cosmic burp, it was the largest explosion ever recorded in the universe, releasing 5 times more energy than the previous record holder. Picture detonating 1 billion trillion atomic bombs simultaneously. That's the scale of fury unleashed here, all from a single black hole's outburst. How does a black hole trigger such devastation? The answer lies in its feeding frenzy. As gas spirals toward the black hole, some gets violently ejected in jets of charged particles moving near light speed. These jets plow through surrounding gas like cosmic blowtorches, carving out bubbles of emptiness in their wake. The Ophiuchus event was so powerful it likely occurred over hundreds of millions of years, a slow-motion eruption that would make supernova look like firecrackers. What's baffling is how little visible evidence remains. No brilliant quasar, no blazing jets, just a ghostly imprint in X-rays, suggesting this monster might have waged its war in the distant past and then gone quiet, leaving only scars as proof of its rage. Yet the Ophiuchus supercluster isn't just a stage for this one spectacular event. Its sheer mass, equivalent to tens of thousands of Milky Ways, makes it a gravitational lighthouse, pulling galaxies into its orbit across millions of light-years. Infrared surveys reveal its tendrils stretching far beyond the central cluster, connecting to neighboring superclusters in a web that might rival even Shapley in scale. Unlike the well-mapped structures of the northern sky, Ophiuchus remains understudied, its secrets obscured by our galaxy's dusty disk. Radio telescopes like the upcoming square-kilometer array promise to pierce this veil, revealing whether this supercluster is an outlier or one of many giants lurking unseen. The implications ripple beyond mere records. The Ophiuchus explosion challenges our understanding of black hole physics, how they grow, how they influence their surroundings, and just how much energy they can unleash. It's a reminder that the universe's most violent events often leave the subtlest traces, hidden in wavelengths invisible to our eyes. And perhaps most humbling of all, if a blast this colossal could go unnoticed until 2020, what other cosmic fireworks might be hiding in plain sight, waiting for the right tools and the curious minds to uncover them? While Laniakea anchors our cosmic neighborhood, another galactic metropolis looms in the opposite direction, the Perseus-Pisces supercluster, a sprawling northern hemisphere counterpart stretching over 300 million light-years. Like a mirror image of our local supercluster, this colossal structure weaves together some of the most famous galaxy clusters into a single interconnected web, revealing how gravity sculpts matter across staggering distances. At its heart lies the Perseus cluster, a bustling hub of over 1,000 galaxies where hot gas glows so brightly in X-rays it outshines the collective light of every star within it. What makes Perseus-Pisces extraordinary isn't just its size, it's the dynamic interplay of forces within its borders. Unlike the relatively sedate motion of galaxies in Laniakea, this supercluster is a theater of cosmic collisions. The Perseus cluster alone hosts one of the most violent black hole eruptions ever recorded, where jets from its central supermassive black hole have carved vast bubbles into the surrounding gas. These cavities, each large enough to hold 50 Milky Ways, ripple outward like shockwaves from an interstellar detonation, redistributing energy across millions of light-years. Meanwhile, the supercluster's western arm connects to the Pisces cluster, a dense knot of galaxies whose peculiar motions suggest an ongoing merger with another massive filament. Mapping this giant required piecing together observations across multiple wavelengths. Optical telescopes captured the starlight from its galaxies, while radio antennas traced the faint glow of hydrogen gas streaming between them. The real breakthrough came when X-ray observatories like Chandra revealed the supercluster's hidden skeleton, threads of million-degree gas outlining the gravitational pathways where galaxies drift like leaves on a river. These hot filaments trace the supercluster's true scale, revealing connections between clusters that optical surveys alone couldn't detect. The Perseus-Pisces supercluster also holds a cosmic time capsule. Along its eastern flank drifts the Andromeda Galaxy, our Milky Way's nearest major neighbor and future collision partner. When we look at Andromeda, we're seeing a galaxy caught in this supercluster's gravitational currents, destined to merge with us in about 4 billion years. This connection makes Perseus-Pisces more than just a distant structure, it's intimately tied to our galactic future. Yet what truly sets this supercluster apart is its role in balancing the cosmic books. Along with Laniakea and Shapley, it forms part of a gravitational triad shaping the large-scale flow of galaxies in our universe. While Laniakea pulls us toward the Great Attractor, Perseus-Pisces exerts a counterbalancing tug, its mass helping to explain why our local cluster of galaxies moves differently than simple expansion models predict. This delicate interplay of forces reminds us that even structures separated by hundreds of millions of light-years remain connected through gravity's invisible web. As telescopes probe deeper into Perseus-Pisces, each new observation peels back another layer. From star-forming galaxies along its faintest filaments to dark matter's elusive grip on its overall shape, this northern titan continues to challenge our understanding of how superclusters evolve. And like all grand cosmic structures, it serves as a humbling reminder, no matter how vast our maps grow, the universe always keeps its next revelation just out of sight. The Sculptor Wall isn't just another distant cosmic curiosity, it's one of the most prominent galactic structures in our own celestial backyard. A vast sheet of galaxies stretching nearly 300 million light-years across the southern skies. Imagine a colossal spine of stars and dark matter, running parallel to the Milky Way's disk like a silent neighbor standing just beyond the fence. What makes this wall extraordinary isn't just its size, but how it reveals the hidden architecture of the universe, acting as a local example of the cosmic web's intricate framework on a scale we can almost grasp. Unlike the more distant Great Walls that span billions of light-years, the Sculptor Wall lies a mere 100 million light-years away, close enough that astronomers can study its individual galaxies in intimate detail. At its heart sits the Sculptor Group, a collection of galaxies including the stunning Silver Dollar Galaxy, its face on spiral arms gleaming like a cosmic jewel. But this isn't just a random scattering of galaxies. The Wall's members move in eerie synchronicity, drifting together through space as if connected by invisible threads. Those threads, of course, are the tendrils of dark matter, the universe's hidden scaffolding that guides galaxies into these vast, flattened structures over billions of years. How does something like the Sculptor Wall even form? The story begins with the aftermath of the Big Bang, where tiny quantum fluctuations in density were amplified by gravity's relentless pull. Regions with slightly more matter drew in even more gas and dark matter, while emptier areas became voids. Over time, this cosmic sorting created vast sheets where galaxies clustered like dew on a spiderweb. The Sculptor Wall is one such sheet, a natural consequence of matter flowing along the dark matter's gravitational pathways, pooling into these stunning two-dimensional structures that partition the universe into cells of emptiness. What's fascinating is how the wall interacts with our own local group of galaxies. While we're not part of the Sculptor Wall itself, its gravitational influence subtly tugs at us, contributing to the complex web of forces that shape our motion through space. Future collisions are inevitable billions of years from now. The Milky Way and the galaxies of the Sculptor Wall may merge into an even larger superstructure, a reminder that these walls aren't static monuments but dynamic, evolving features of the cosmos. The Sculptor Wall also serves as a cosmic laboratory. Its relative proximity lets astronomers study how galaxies behave in dense environments versus sparse ones, revealing how walls nurture or stifle star formation. Some galaxies here are being slowly stripped of their gas by the wall's collective gravity, quenching their ability to birth new stars. Others, caught in the web's quieter outskirts, continue to sparkle with young blue stars. This diversity offers a snapshot of galactic life cycles, all within the same vast structure. Yet for all its grandeur, the sculptor wall is just one thread in a tapestry that stretches across the entire observable universe. It reminds us that the cosmos builds its largest structures with a mixture of elegance and chaos, dark matter's invisible hand guiding galaxies into patterns that, from the right perspective, reveal the universe's hidden skeleton. And as telescopes grow ever more powerful, each new observation peels back another layer, showing us that even in our own cosmic neighborhood, the universe's grand design is written in walls of fire and shadow. For decades, astronomers operated under a fundamental assumption that when you zoom out far enough, the universe should smooth out into a featureless expanse. This idea, known as the cosmological principle, suggests that beyond scales of about 300 million light-years, matter should distribute evenly, with no single structure dominating the cosmic landscape. Yet as our telescopes peer deeper and our maps grow more detailed, the universe keeps defying this expectation in spectacular fashion, presenting us with structures so vast they threaten to rewrite cosmology's foundational rules. Take the Hercules-Corona Borealis Great Wall, spanning 10 billion light-years, roughly a tenth of the observable universe, or the giant Giabi Ring, a near-perfect circle of gamma-ray bursts 5.6 billion light-years across. These aren't just outliers, they're cosmic anomalies that challenge our understanding of how matter organizes itself. Imagine shaking a snow globe and watching the flakes settle into a single, continent-sized clump instead of scattering evenly. That's the level of irregularity we're seeing on the grandest scales. The tension lies in the timeline. According to our best models, gravity needs roughly 13.8 billion years, the universe's current age, to sculpt matter into coherent structures. Yet these colossal formations appear too early, too organized, as if the cosmos cheated by jump-starting their growth. One radical theory suggests dark matter, the invisible glue holding structures together, might have clumped faster than expected in the universe's hotter, denser youth. Another proposes that the seeds for these giants were planted during inflation, the explosive expansion moments after the Big Bang, when quantum fluctuations stretched to cosmic proportions. Even more puzzling is what these structures imply about the universe's geometry. If matter clusters into continent-scale formations beyond the predicted homogeneity threshold, does the cosmological principle need revising? Some theorists argue we're seeing statistical flukes, rare overdensities in an otherwise uniform cosmos, while others whisper about more exotic possibilities, like our universe being a local bubble within a far vaster, uneven multiverse. The stakes couldn't be higher. If the end of greatness doesn't arrive where predicted, it could force us to rethink everything from dark energy's influence to the very nature of gravity itself. Future telescopes like the ESA's Euclid and NASA's Nancy Grace Roman Space Telescope will map billions of galaxies, probing whether these giants are cosmic accidents or signs of deeper physics at work. Until then, each colossal structure we uncover serves as both a triumph and a provocation, proof that the universe's grandest designs remain gloriously, mysteriously unresolved. From galaxies clustered into walls wider than billions of light-years to voids so empty they distort the fabric of space itself, the universe's largest structures don't just defy imagination, they rewrite the rules of reality. Every time we think we've grasped the limits of cosmic scale, the cosmos reveals something grander. Superclusters moving in unison toward unseen forces, ancient protoclusters that formed impossibly early, and celestial formations so vast they make our entire observable universe feel like a single brushstroke in an infinite painting. These aren't just scientific curiosities, they're humbling reminders that everything we know is dwarfed by the sheer audacity of existence. What's truly staggering is how these discoveries force us to rethink fundamental assumptions. The cosmological principle, the idea that the universe should look roughly the same everywhere at large scales, crumbles when confronted with titans like the Hercules-Corona Borealis Great Wall or the giant Jubby Ring. Their very existence suggests gaps in our understanding of gravity, dark matter, even the Big Bang itself. Are these structures statistical flukes or clues to deeper physics? Do they hint at a multiverse, unseen dimensions, or forces we haven't yet named? Every answer we uncover seems to open 3 new questions, proving that the universe's greatest gift is its endless capacity to astonish. But here's the most beautiful paradox. While these discoveries highlight how small we are, they also showcase humanity's relentless curiosity. The fact that we've mapped galaxies behind the Milky Way's dust, detected whispers from the cosmic microwave background, and traced invisible dark matter's grip on the cosmos speaks to something extraordinary: our refusal to stop exploring. Whether it's the eerie silence of the Boots void or the violent fury of the Ophiuchus supercluster's black hole, each revelation is a testament to science's power to turn the unknown into the known, one observation at a time. So which of these cosmic titans left you breathless? Was it the Great Attractor's invisible pull, the Saraswati supercluster's precocious size, or the cold spot's multiverse whispers? Drop your favorites in the comments, and if you're craving more deep dives into the universe's mysteries, let me know what cosmic puzzles we should unravel next. After all, the universe isn't done surprising us, and neither are we. The next great discovery might be hiding in plain sight, waiting for someone like you to look up and